It's afternoon for most of you. It's early morning for me here. I'm Srinivas Palanki, and I'm a professor at the University of South Alabama, and I will give this talk today on energy sources for the future.
Muted.
By the way, and you can interrupt me anytime. If you have questions in the middle, feel free to send me a note in the chat mode, and I will stop and respond. So again, this is a rather, there are a lot of things to cover here. So I'm not going to cover every aspect here. I just want to give you an idea of what the issues are if you are looking at the hydrogen economy. Again, there are a lot of energy sources in the future, and one of the solutions that people are talking about is using hydrogen as a fuel. And so there are a lot of issues that arise once you make that decision. And I just sort of briefly hit on each of these issues. So why hydrogen? Hydrogen is the most abundant element in the universe. So that could be significantly fewer environmental issues dealing with hydrogen rather than some other hydrocarbon. Now, the problem really is, even though it's the most abundant element in the universe, it's found in bound form only on Earth. So it is found as part of water, so it is H2O. Hydrogen is not really very abundant in free form. And so you will find it in water, you will find it in biomass, it might be there in fossil fuels. So all the hydrocarbons have hydrogen in it. And so there is an issue of extracting hydrogen. Here are some more reasons. It is available easily. Again, if you're willing to work with the bound form, it can be pollution free if it's produced from the right source. And again, hydrogen, hydrocarbons, petroleum or fossil type fuels are available in a lot of places in the world where there's turmoil. And so if you switch to a different source, then this is potentially a peace dividend. And it is at least theoretically possible to replace all of gasoline and eliminate all CO2 emissions, again, depending on what the source is. So there are some barriers to the hydrogen economy. Now, hydrogen is an energy carrier. It is not an energy source. There is some energy required to produce hydrogen. It doesn't come for free. And so if you are trying to, let's say, get a certain amount of energy, let's say you're trying to get, let's say, a megajoule of energy, then the question you have to ask is how much energy do you need to produce that? Just to give you a rough idea, if you are making fossil fuels, the amount of energy required to make, say, a gallon of gasoline, or petrol, you normally use about 10 to 12% of that energy to produce that. So it's actually pretty efficient. You're able to sort of recover 88 to 90% of the energy that you have. So you have to think in terms of competing with that as a benchmark. There's already an existing infrastructure based on fossil fuels. So there is, again, the process of producing gasoline from crude oil is well known. It's been around for more than 100 years. And so if you're thinking of a new source of energy, then the question is, can we use part of that existing infrastructure? And if one could use part of that structure, then the buy-in would be faster. It is easier to integrate into an existing infrastructure than to build one from scratch. There is a public perception of hydrogen safety. There is a perception that hydrogen is dangerous, it's explosive. And so, again, it's not enough to have a good engineering solution. The public also has to perceive it as good, and they should be willing to use it. And if that doesn't happen, then it's not going to fly. And finally, the engineering design and operation issues have not been completely worked out. Now, again, there are two different sources of hydrogen. One is renewable, and so one could get it from biomass, which could mean get it from, say, ethanol that you're getting from corn or sugarcane. One could get it from methane, which is, one could get that through biogas, or one could get it from glycerol. So if you're making biodiesel, then through transesterification of a vegetable oil, then a byproduct of that is glycerol, and one could then potentially say, well, what do I do with the glycerol? Maybe I can extract the hydrogen out of that and use that. So that's one way. Another way could be to use, do electrolysis of water. So you take water and split hydrogen and oxygen out of that and use the hydrogen. Another source is a non-renewable source, which means this is stuff that will eventually run out. So like a fossil fuel. So one could use, say, a fossil fuel like gasoline. One could use coal or maybe natural gas. Now again, this is using a non-renewable source is an intermediate solution. If one was using that, then you have to realize that these will run out, and so you run into the same problem that people are talking about fossil fuels. So if you have a whole infrastructure that is based on making hydrogen from, say, crude oil or gasoline, then that is going to run out. Now, the advantage, of course, is that you are integrating into an existing infrastructure, and so you're using part of an existing infrastructure. So that is potentially cheaper in the short run. In the long run, one has to switch to a renewable resource, such as biomass or just use water. Now, let me switch gears a little bit. So what is a fuel cell? So if you have hydrogen, you would want to generate power from that. You have to use a device called a fuel cell. And what is a fuel cell? This is essentially a battery. But when one thinks of a battery, one thinks of what is called a dry cell, which means you have electrolyte, which is a paste. But this is a little different. It does not run down as long as it is supplied with fuel. This was developed a long time ago in 1839. And essentially, you have hydrogen, which is going through a semi-permeable membrane. And so the hydrogen ions diffuse through the membrane, and then you've got electrons going basically across to complete electric circuit. And the flow of electrons essentially generates electricity. And the hydrogen ions will combine with oxygen at the other end, and you end up with a byproduct, which is water. And so there are no moving parts. It's a quiet operation, and it has been used since at least the late 50s, early 60s in space applications. Now, just to give you some idea of numbers, if you're making gasoline from oil, you're looking at efficiencies from 73 to 90%. Electricity from coal, 29 to 35%. And hydrogen from natural gas is 72 to 85%. So you can see there are, it doesn't come for free. And so what you have existing currently from fossil fuels is actually pretty efficient. And if you look at especially gasoline from oil. Now again, let's just look at power systems. If you're using pure hydrogen in a fuel cell, and efficiency again is not 100%, you will lose some. So 80 to 90% efficiency. An internal combustion engine has an efficiency of, say, 15 to 20%, and the U.S. electric grid is about 33%. So that's what it really takes. So we can see, the efficiencies start to come down in several of the existing processes. So what I'm going to do is I'm going to look at two different aspects today. One is, how do we produce hydrogen from a hydrocarbon source? So we are going to look at something that is potentially non-renewable, but one could then replace the hydrocarbon source with a renewable source. And so you sort of start with an existing infrastructure, and then you sort of build backwards on that. And the second issue we'll look at is, how do you use it in the fuel cell to produce power? And so there are a lot of issues once you make that choice that you're going to go to the hydrogen economy. There are a lot of technologies one has to look at to make this work. In particular, we have to look at how do we design a reactor that will take a hydrocarbon source and produce hydrogen from it. And then once we have that, then how do you design a fuel cell system? And then, of course, then you have to integrate the two so that you, on the one end of the pipe, you have a hydrocarbon source, and on the other end of the pipe, you are getting power. And hopefully with very few environmental issues. Are there any questions so far? And I've gone on for about 7 or 8 minutes. I see a question here. There is a voice problem.
No questions here.
I see something on chat here. It says, are you able to hear me at the other end?
It is. I can hear you, sir.
Okay, because I saw here transmission is okay. It might be a temporary problem. Oh, with on the other end. Okay, all right. Okay, let me just go on then. Okay, so hydrogen can be produced from hydrocarbons in 2 different ways. One can do steam reforming, or one can do partial oxidation. So in steam reforming, steam reacts essentially. You have steam, and you react that with a hydrocarbon, and that forms carbon monoxide, carbon dioxide, and hydrogen. This reaction is endothermic, and so energy must be supplied for this reaction. Now, what is partial oxidation? So partial oxidation is hydrocarbon reacting with oxygen, and if you have excess of oxygen, then you're going to have, you essentially have combustion. And so what we do is for partial oxidation, you want to use a quantity of oxygen that is inadequate. So we use less. And again, this has to be done in conjunction with a catalyst. So you don't get to temperatures that are as high as you would see in combustion. This reaction is exothermic, and so it is not necessary to supply energy for this reaction. Once it gets going, it's giving off heat, and so in some ways it is self-sustaining. And then you have autothermal reforming, which is a combination of both steam reforming and partial oxidation. And if it is done right, the idea is that you do some partial oxidation and you produce enough energy through that reaction so that it can support the endothermic reaction of steam reforming where energy is required. And so it's a combination. Now let's look at some reactions here. So if you look at steam reforming of methane, you have essentially these 3 reactions occurring. And so you can see methane reacts with steam, giving you carbon monoxide and then 3 moles of hydrogen. Now usually in conjunction with this, there's also another reaction goes on, which is called the water gas shift reaction. So carbon monoxide is reacting with water to give you carbon dioxide and hydrogen. So you get an additional mole of hydrogen if you do it like this. This is important in some fuel cells. For example, if you look at polymer electrolyte membrane fuel cells, which are fairly popular now, and if you look at the electric cars that are coming out, most of them run on PEM fuel cells. The big advantage being that they run at relatively low temperatures, 80 to 90 degrees Celsius. Now the problem with these fuel cells is they cannot tolerate carbon monoxide levels that are higher than say 50 to 100 parts per million. And so it's important to not have any CO in your exit stream. And so one has to make sure this reaction goes to completion if possible. And so that there's no carbon monoxide and all the monoxide has been converted to dioxide. There's also another reaction that goes on, and again, note that all of these reactions are reversible. So the carbon dioxide and the hydrogen could recombine to form methane and water. And so in some ways, this is a loss in efficiency if this happens. The reaction temperature, pressure, and catalyst determine which reactions dominate and how much hydrogen and carbon monoxide is produced. And so one can play with there are parameters one can play with. You can decide what temperature, what pressure, and what catalyst to use. And depending on your choice, you'll have different amounts of hydrogen being produced. So that's essentially a design issue then. Now one doesn't have to use methane, one could use a higher hydrocarbon. And you can see sort of similar reactions happen. So you see water gas shift happening here. You see that this is sort of the main overall reaction, that your higher hydrocarbon is reacting with steam to produce hydrogen. And then the other reactions also go on, the reaction to form methane, and that can sort of happen through CO as well as through CO2. And once again, there are parameters one can play with. You've got temperature, pressure, and catalyst, and you have to decide what levels you're going to set the temperature and the pressure, and which catalyst you're going to use for different reactions to dominate. Now, one doesn't have to use sort of an alkane to do this, or a hydrocarbon. One could also use an alcohol. So one popular one that is being considered is the steam reforming of methanol. And so instead of using hydrocarbon, one is using an alcohol. So you can see methanol reacts with water to give you carbon dioxide and hydrogen. Now methanol itself can decompose to carbon monoxide and hydrogen. And again, it depends on what temperature you're running this at. Realize that you're talking about 400 to 500 Kelvin for this reaction. And so at those elevated temperatures, the molecules themselves will start to decompose. So you can have that in addition to steam reforming. And then you also have water gas shift. And once again, we have sort of parameters we can vary to decide on the composition of the exit stream. Now, another way of doing this is partial oxidation, like I have mentioned earlier. So one could take a hydrocarbon, react it with an inadequate amount of oxygen to give you carbon monoxide and hydrogen. Now, the thermodynamic characteristics of individual reactions depend on which compound you're using. It depends on this molecule, which hydrocarbon you're using. And so steam reforming reactions are endothermic. The water gas shift reaction is mildly exothermic, and the partial oxidation reaction is highly exothermic. And so essentially, from a thermodynamic point of view, achievable conversion is determined by equilibrium. And the equilibrium constants change very significantly with temperature. And so this is sort of a parameter that is a sort of under your control. Depending on which reaction you would prefer, you can vary that. And normally, water gas shift reaction is favored at lower temperatures, and steam reforming is favored at higher temperatures. That's sort of like Le Chatelier's principle. And so one can play around with these conditions to make things happen. And so I'm going to go over this very quickly. Essentially, if you have a reaction like this, A plus B going to C plus D, then the equilibrium constant K is a key thermodynamic parameter that one has to consider. And this is related to the Gibbs free energy, which is usually represented by delta G. And so K is represented to delta G by this equation. And again, this is sort of standard thermo, so I'm going to go over it very quickly. So the Gibbs free energy is a thermodynamic potential that measures the useful work that can be obtained from an isothermal, isobaric thermodynamic system. So if you have a system at constant temperature, constant pressure, then how much work can we get out of it? And so this sort of gives you a bound. So it's the maximum amount of non-expansion work that you can extract from the system. And so clearly this is, you will get less than that. This is the most you can get. And the key thing to look at is really this. So if delta G is less than 0, that means the forward reaction is going to be favored. And if delta G is greater than 0, then the reverse reaction is favored. So again, one has to see, for example, if you're looking at water gas shift, so are you producing water from hydrogen, or are you using water to make hydrogen? You can sort of look at that. And so here is a quick example. So if you look at this water gas shift reaction, and again I threw in some numbers here. My slides are available, and I'll if you want these slides, just send me an email and I'll send them to you. So I'll just go over these numbers very quickly. And so one can see that at a high temperature and a high pressure, the Gibbs free energy of formation is given by these numbers. And so you can see that the delta G is negative, and hence K is going to be 1.44, which means the forward reaction is favored, which means this reaction will go in this direction. Now, if you choose a different temperature and pressure, it might happen that the reaction goes in this direction. And so one typically looks at diagrams like this to see what the effect of temperature would be on the reaction. Now let's look at design equations. So essentially, thermodynamic considerations tell you the reaction is going to happen or not in the condition and the pressure and temperature that you've chosen. And so if you're not producing what you want at that temperature and pressure, no matter what you do with reactor design, you're not going to get it. You're not going to get the product you want. So one has to check that first. And once that's been checked, then the big question to ask is, how large will my reactor be? So do I need a cubic meter, or do I need something much smaller, say 1/10 of a cubic meter, or do I need something huge like 10 or 20 cubic meters? And that's sort of the kind of question you want to ask. Clearly, if you're thinking of a portable application, if you're thinking of an application with a laptop, let's say you want power for a laptop, that clearly has to be something small, something the size of a AA battery, or 4 or 5 of AA batteries. You clearly cannot have a power source that is bigger than your laptop itself. So that's a design consideration. Now, if you look at this gas phase reaction, in general, moles are not conserved, because there's a reaction going on. The number of moles of reactants going in is not equal to the moles of product coming out. Also, the volumetric flow rate in is not equal to volumetric flow rate out, because there could be a considerable change in moles and hence a considerable change in volumetric flow rate. And the reaction rate with respect to species A, B, C, and D are related via the stoichiometry. So if you know the reaction rate with respect to A, you can back out the reaction rate with respect to all other species by knowing the stoichiometric coefficients, these little a, little b, little c, and little d. And so one can write out a mole balance equation. So if Fa is the moles of A divided by time, so it's the molar flow rate of A, and Ra is the reaction rate of A. So dFA, dSV is the reactor volume. So you're sort of doing a balance along the length in some sense, if the area of cross section is the same. So the moles of A will change as you go along the length, and that relationship is given by this equation. So dFA dV is Ra. And one could write out a similar mole balance for B, C, and D. Now, the reaction rates of A, B, C, and D are related by stoichiometry. I had in the previous slide minus Ra over A is minus Rb over B equals Rc over C equals Rd over D. And so all of these could be written in terms of Ra, the reaction rate with respect to A. And so if you know the reaction rate with respect to one species, then you can compute the rest from stoichiometry. Now, once you do that, you need to know what Ra is. So this rate law, Ra is called the rate law. This is usually determined from experiments. It's hard to get this from first principles. So for example, if Ra is minus Kc ACB, then Rb is related to Ra through this stoichiometry, right? So minus Ra over A is minus Rb over B. And so Rb is going to be B over A Ra. So that's how we get this. And the same way for Rc and Rd. Now the problem is, if you look here, on the left-hand side you have molar flow rates, right? And on the right-hand side you have this reaction rate, which is in concentrations. Concentration of A and B. And so one has to do some unit conversions. This is really bookkeeping. So you want to convert everything into molar flow rate so that everything is then consistent, and these equations can then be integrated so that you can then find out what the volume is. And so we go through some bookkeeping essentially. I'm going to skip through this very quickly. So you can see that I can write concentration of A in terms of the molar flow rates of A, B, C, and D, as well as pressure and temperature. And so I made some assumptions. I made an assumption that the gases are ideal, which is actually not that bad. Typically, you're operating this reactor at high temperature, and pressures are usually moderate. Again, it would be hard to imagine operating this sort of a device at very high pressure and then expecting people to use it for, say, a portable application, or even a sort of a fixed application like a home power system. So you wouldn't consider pressures above 3 or 4 atmosphere anyway. And so at the slope, low to moderate pressure and high temperatures, an ideal gas assumption is actually valid. And so we can write this out for A, B, C, and D. And so again, it's again bookkeeping. So K, C, A, C, D, this looks simple. But if you write this in terms of molar flow rates instead of concentrations, you'll see that the expressions become a little more complicated. And one can write out these balances for B, C, and D as well. So essentially, you have this algorithm now for mole balances in the reactor. And again, I basically derived the equations for the mole balances if there's only one reaction. If you have multiple reactions, it's a bookkeeping issue. You're basically you're making sure that you're essentially using conservation of mass. And so you go through this algorithm to write out equations that sort of look like this for all the species in all the reactions using this procedure. And once you do that, you are going to end up with a set of ordinary differential equations. And so you'll end up with something that looks like dFi dV equals some function of all the molar flow rates, temperature, and pressure. And I is the variable, the number of species. So if you have 5 species, you have 5 equations. And so then these have to be solved. And typically this solution is found numerically because the equations tend to be coupled and they're nonlinear, and analytical solutions are rarely available. Now, there are a couple more things one has to worry about. One is you see that, for example, here you had pressure and temperature, and the temperature will appear here as well. This rate constant is usually a function of temperature. So if one uses like an Arrhenius type expression, so K would be something like this. And if you have multiple reactions, then each of those reactions would have rate constants, which would have expressions like this. So the equations are highly nonlinear in general. And so if you have gases flowing through a packed bed, then pressure is going to change as you go down. And there are 2 reasons why pressure would change. So pressure would decrease as you go down just through, this is the resistance to fluid flow. And that's sort of intuitive. As you have a gas going through a packed bed, if you start at 2 atmospheres at the beginning, then at the tail end you may have 1.5 atmospheres. There will be some drop in pressure just because of resistance to flow. But pressure will also change due to the change of total number of the moles. I had told you earlier that moles are not conserved. The number of moles coming in is not equal to the number of moles going out. And so if you had AA plus BB going to CC plus DD, then, and if let's say you had complete conversion, then A plus B is not equal in general to C plus D. So the number of moles coming out could be substantially different. It could be more, it could be less, depending on what the reaction is. And so you will have change in pressure just because the moles of gas that you have changed. And so we need an additional equation so pressure is essentially not constant, right? So P in is not equal to P out. And so if we have this pipe with packing, then and this is P in, this is P out. The pressure in is not the same. Pressure will change along this length. And so a popular equation to use would be the Ergun equation. You can see there are two terms. This is usually dominant for laminar flow, and this is more dominant for turbulent flow. And so this sort of gives you a relationship between pressure and other parameters of the bed. You can see there is a bed porosity involved, there is a density involved, there is viscosity involved, and so one has to know what these are. And again, I'm going to go through this very quickly. Ergun equation is available in any standard undergraduate chemical engineering textbook. But again, the point that I'm trying to make is pressure drop is a function of the flow as well as the parameters of the bed. Now, due to the reaction, the gas mixture composition itself changes, right? Because A and D are converting to C and D if there was just one reaction going on, and again, typically there are multiple reactions going on. So gas mixture composition is changing. So if you look at any point in this bed, the composition here is different from the composition here, which is different from the composition here, and so on. And because the composition is changing, the gas mixture density will change, the gas mixture viscosity will change, and superficial velocity will also change. All of these changes have an effect on the pressure, because if you go back here, you can see here, this is the density, this is the viscosity, and this is the mass superficial velocity. So this is changing along the length. So these are not constants. And so one has to go and look for ways of calculating the mixture density as well as the mixture viscosity as a function of composition. And so rho is not a constant, and then viscosity is also not a constant. And so one has to look for some sort of estimation methods that will determine these as a function of composition. And so you are essentially, by solving the mole balance equations, you are determining composition. And then you have to look for some other correlations that will correlate composition to viscosity and composition to density. Now, again, the reactions are not isothermal. They could be exothermic, they could be endothermic. And so we need an energy balance as well. And so again, energy balance would mean, let's say you're providing heat. Let's say you're doing only steam reforming. Those are endothermic, you provide heat. So you have this packed bed now, and around it you're going to have some sort of a jacket which will provide heat. And one way to do that could be to maybe burn some of your fuel in here. So you're doing combustion in the jacket and then reforming in the reactor. And then there is heat transfer from the jacket to the reactor. So you'll have a term that involves heat transfer, and then you have another term which involves heat of reaction. So you have at least two terms. And then there is a flow term that shows up here. And so you need an energy balance as well. So temperature can change along, so this temperature is changing along the length. And so you need one more equation. And again, this is a standard energy balance equation, so I'm not going to dwell too much on it. It's just that one has to keep track of it. So I'm going to skip through this. Now there are methods to estimate the heat transfer coefficient. And again, this is from a standard heat transfer textbook that we have used. And so there is an HI and an HIO, and then you do overall heat transfer coefficient U based on these. And so I'm not going to go over this in detail. And so essentially what you have to do is you have to solve the energy balance equation and the pressure balance equation simultaneously with the mole balance equation. So you're looking at equations like dFi dV equals some function of temperature, pressure, and composition. And in conjunction with that, you're solving this dP dV equation, which is another function, and then also dt dV, which is yet another function. So you have several of these. This is no, is again a running variable. So you have several equations. So if you have, say, 10 species, then you will have 12 equations to solve. 10 plus 2, the other 2 being pressure and temperature, and you have to do this all simultaneously. So you're looking at a fairly substantial numerical problem now. Now, I had said earlier that the density is not constant, and so one has to determine density as a function of composition. And the easy way again is to use ideal gas law. This usually works quite well because the temperatures are high and pressures are low. And so, essentially you can calculate the mixture density by using a mixture molecular weight. So you find the average molecular weight at any given point, and you can find that out by knowing composition. And then you use the ideal gas law, and you can find out the mixture density. Now, the viscosity also is not a constant. And so, you can see that is a function of, so viscosity varies with volume, and so one has to know what that relationship is. Usually, again, you have hydrogen present in the gas mixture, so the mole average can lead to significant errors because hydrogen is much lighter than all other gases that you have, which is carbon dioxide, carbon monoxide, your hydrocarbon itself, say methane, and whatever higher hydrocarbons you have, and so it is not a good idea to find the mole average. And there are methods available. And again, I'm going to skip through this. Essentially, all I say is there are methods available in the literature that will estimate viscosity of a gas mixture. Like the one that we use commonly is the method of Wilk. You can find this in any thermodynamic book, and this does better than the mole average. And so again, one has to look up methods like this because if you have this pipe flow, your viscosity in and your viscosity out can be very different, and so this will change along the length, and you have to put this relationship in your Ergun equation. Now, there's also a need for a catalyst. The reforming reactions are conducted in the presence of a solid catalyst, and so typically you're looking at catalyst particles, and I'm just sort of drawing a blowing this up, and these are porous, and then usually you have some sort of a noble metal like platinum or palladium that coat the pores, and the reaction actually happens on the on that large surface area that is generated in these porous catalysts, and so usually you're using reforming catalysts are metals like nickel, platinum, and palladium, which are coated on supports such as alumina or ceria. And the most important characteristic of a catalyst is its ability to selectively enhance the rate of a certain reaction. And so if you have 4 or 5 reactions that are possible, the idea is to choose a catalyst that will enhance the rate of the desirable one, and then and other ones, while not affecting other ones. And how one does this sort of from first principles is not well understood. In general, catalyst preparation is done through extensive trial and error. And so you basically try things out and see which is the one that works best. Now again, if you consider a catalyst particle, then if you have a particle like that, there are several, and let's say there is a pore, and there are several things that are happening. So if we have a reactant A, then this molecule has to first come to the surface, and then it may get adsorbed onto that surface, and then you have diffusion. So then there is diffusion. So there could be resistance to this diffusion. There could be temperature gradients, and so let me go through this. So there could be temperature gradients within the particle itself, and then you could have a film gradient between the outer surface and the main gas stream. And so if you have this, and you have, let's say, a film around it, then there could be a temperature gradient here itself. There could be a film resistance because of the concentration gradient across the gas film surrounding the particle. And so usually, depending upon what the reaction is, whether it is slow or fast, these different effects play a role. And depending upon which ones dominate, your reaction kinetics could look different. And so again, depending on what sort of catalyst you have and how it is behaving and which reaction is happening, you can have modifications to the reaction itself. And so again, one has to keep that in mind when one does that. And again, this now you're getting into surface chemistry, and the rate expressions will vary depending upon which one dominates. And you can see the rate expression can become pretty complicated depending upon how this is done. Now, usually, again, there is no good way to determine a priori which mechanism dominates for, say, a reaction like that. So usually what's done is you postulate a mechanism, and you say, this is what I think is happening. The molecule diffuses through a film, goes on the surface, and then it diffuses into the pore, and then a reaction happens on the pore surface, and then the product molecule is going to diffuse out of the pore and then out into the bulk. And so depending on, so I'm very quickly going to skip through this. So basically, if the actual mechanism of the action is known, one can write an accurate expression from first principles, but usually that's not the case. And so you end up postulating a mechanism, and then there are a large number of parameters that will end up based on this postulate, and it is common to then do some sort of curve fitting to fit parameters. Now, it is possible for several different rate expressions to fit this data equally well, and so the question is, which one do we use? And usually from an engineering perspective, we use the one that's the simplest. And so one has to be a little careful in extrapolating data when you're doing this sort of modeling, because it's really parameters that you're fitting, large number of parameters. So interpolating such an expression, using such an expression is okay. If you're extrapolating, if you're going outside the range of pressure and temperature where this was developed, it's a bit questionable if the reaction rate is even accurate. So now let's change gears a little bit and look at the relationship between hydrogen flow and current. So essentially, we found the design equations for a reformer, and so you have expressions like that, and some other expression, something like that, and then all this will, you have to solve these equations simultaneously, and that will give you the reactor volume. So what you have done is you have determined that if I have a certain reactant and I operate at certain pressures and temperatures, then which will of course vary along the length, then I end up with a certain amount of hydrogen. So by varying the volume, one could then determine how much hydrogen is produced. So now the question is, what do we do with the hydrogen? So that is now going to go through. So once you have this, you will then now go through a fuel cell, which will then produce power, and then it produces water as a byproduct using the hydrogen that came out of the fuel cell. And then you'll use there to combine the hydrogen and the oxygen. So now we are looking at this part, the fuel cell part. And there's a relationship between the flow rate of hydrogen and the current that's produced. Current is flow of electrons, and you essentially have hydrogen ions going through this membrane, and then you have sort of a flow. Let me do this again. So you have hydrogen ions going through this membrane, and then you have electrons that will sort of go that way. And so this flow electrons through the electrical circuit is giving you current. So there's a relationship between this current and the flow of hydrogen, and it's given by this equation where this F is the Faraday's constant. Now there is a relation between current and voltage, and what happens in a fuel cell is you're going to have some loss in efficiency. You would like, in the ideal situation, the theoretical optimum would be 1.23 volts for a hydrogen fuel cell, and this would be realized at all operating currents. So no matter what the current is, the voltage should remain fixed. This is called the open circuit voltage. But the reality is, when you are operating a fuel cell, you have an effect which is known as polarization, and essentially this represents the loss of efficiency that you have in a fuel cell. So you can see that this is where you want to be. This is ideal, but there will be losses. So there will be losses due to, essentially due to heat. There will be losses due to the concentration gradient, and then there's losses due to this activation. And so depending upon, the y-axis, the x-axis here is current density, which is the current divided by area, and this is your voltage. And so you can see that if you're operating at a certain current density, then the voltage that you have is lower. So the open circuit voltage is higher than your operating voltage. So this is the theoretical voltage, this is actual. So you can see that depending upon which current density you operate at, your voltage will actually go up or go down. And so you're losing a certain amount of efficiency by going to higher currents. And so you would like to operate at as high a current density as possible, but then you're giving up voltage for that. And so power is current multiplied by voltage. So increasing current won't necessarily give you increasing power because your voltage is dropping. And so again, I'm going to skip through this since I have only 10 minutes. So I'll just skip through that. All I'm saying is power is your voltage multiplied by your current, and N is the number of cells. So that's the total current that you're getting. And so power is voltage times current. And when you increase the current, so then current is, let me do this again. So power is voltage times current. So when current is increasing, voltage is decreasing. So this power may increase or decrease depending upon whether the increase in current compensates for the decreasing in voltage or not. So depending on how much the current increases and how much the voltage drops, power changes. So normally if you look at a power versus current density curve, it's going to initially go up and then it will come down. And so there is sort of an optimum point in your polarization curve where you should operate. So now efficiency of a fuel cell is often, this is considered one of the primary benefits of technology. But even though this is true in principle, one has to actually look at the efficiency of the fuel cell stack and the efficiency of the fuel cell system. Remember, in the entire system, we also have a reformer and then a fuel cell. And so the question is, what is the efficiency? It's important to not only look at efficiency of that, but also efficiency of the whole thing. Because finally, you have some sort of hydrocarbon fuel, and then you're getting power out of that. And so efficiency of this system is what really drives the system. Now, typical values of efficiency for an internal combustion engine are between 15 and 25%. So this is your car. And so the question is, can you do better than this? So if you have an electric car that runs on hydrogen, will you do better than this? if we assume the hydrogen is coming from gasoline. Now, these values are representative of the output efficiency at wheels of the vehicle. So if you have a fuel cell that is operating on pure hydrogen, so let's say you somehow got the hydrogen, then typically the efficiencies break down like this. The fuel cell efficiency is 40 to 50%. The air compression efficiency, remember you have, fuel cell, you're forcing gases to this, so there is a compressor that is involved here to make the gas go from left to right. And then you have an inverter efficiency, electric motor. These are actually pretty efficient, so you're not losing much there. And so overall efficiency is 30 to 40%. And so on the face of it, it looks like that's better than this. But realize that you also have to use a reformer to get the hydrogen. And so if you take that in mind, these are further reduced by 60 to 70%. And so your overall efficiency then ends up being 20 to 29%. So you can see you're sort of in this range. And so you're really not significantly better off than an internal combustion engine if you're looking at a system that operates on fuel cells that use a reformer, which is reforming standard hydrocarbon fuel. So let me quickly go through this example. In the literature, we found somebody had built this reformer for methanol. This was in the literature. There is this group in China that had built this. And we actually tried to use the design equations just again from the literature. So the reaction kinetics are known. This is from Pepley. And if you write out the mole balances, if you write out the pressure balance, you write out the temperature balance, and then you go through this entire calculation and also do the heat transfer calculation, assuming that we are burning some of the methanol in the jacket, then you can see that the experimental results, and this is from literature, these are the open circles, and this is our simulation results at various steam to methanol ratios. You can see the experiments and the theory, they line up quite well. We didn't adjust any parameters. We just used expressions from the literature. And so one can use this as a means of doing design. This is the length that they had used. They had used 7 centimeters length. And so the pressure drop in this case turned out to be negligible. So the increase in moles, the pressure increase due to increasing moles was roughly offset by the pressure drop due to fluid flow. And one can use this simulation model now to optimize. For example, we found that if we went to a slightly higher length, if we went to 10 centimeters, you could get away by operating at a lower temperature, and you could get the same hydrogen flow rate that you were getting from the conditions that the authors had suggested. So here are some numbers on fuel cell stacks. So if we have 25 cells, and if that's our hydrogen flow rate, then you can get enough hydrogen to get 20 watts of power, 20 to 25 watts. That's what I think the authors had wanted. And so I'm quickly going to put some conclusions here. One can use the fundamental principles of chemical engineering for addressing this design challenge. Essentially, you're looking at integration of reaction engineering, heat transfer, fluid mechanics, and some mass transfer. And again, everything I showed you is from standard undergraduate textbooks, but it can be used to solve a problem which is of interest at the graduate level. And we are looking at several different extensions to this, look at different hydrocarbons, different power requirements, different fuel cells, and so on. And if you go to my website, you can see we have several journal publications just using this basic idea. And what I went over is basically what we teach in a graduate level reactor design class. And so I'm going to stop here, and if there are questions, please let me know. If you would like a copy of these slides, please send me an email. And if you go to Google and type my name, I'm easy to find. There are not that many Srinivas Palankis in the world. And so just say Srinivas Palanki and I don't know, maybe South Alabama, you'll find me easily. Send me an email and I can send you these slides. Thank you.
Sir, there is one question.
Okay.
What about the H2 production from renewable resource?
So the basic idea is still the same. You're still looking at, so for example, one idea that we looked at was, well, we looked at two different things. One was using a source like ethanol. And this has been popular, though I think the ideas are sort of dying down now. There was a big move in the US to produce ethanol from corn. If you look at a country like Brazil, they produce ethanol from sugarcane. So that's a renewable resource. You're essentially, what you're doing is you're taking solar energy and you're growing plants with it. And so you have converted solar energy to chemical energy, which is sort of in a stored form. And if you can process that into a form you can use, and usually most of the time you want the fuels to be liquid. So you're taking essentially a solid fuel and converting it to a liquid fuel. So converting corn or sugarcane, into ethanol. So you're basically converting sugar to ethanol. Now you have a liquid fuel. So instead of burning the ethanol to produce energy, one could run this through the reformer, make hydrogen, and run that through the fuel cell. So that is now renewable. So you're using the same basic idea to do this. The other angle we looked at was biodiesel. So if you have something like vegetable oil. So again, vegetable oil is a sort of a way of converting solar energy into chemical energy, right? So you can't take solar energy and produces oil. And so if you transesterify this oil, you get biodiesel, which can be used as a renewable fuel. But then a byproduct of this is glycerol. So we actually ran experiments with this too. We took the glycerol and we steam reformed it. And when you steam reform it, you get hydrogen. So again, you're not wasting your glycerol. You have a use for it. So again, the idea is to sort of use as much of the existing infrastructure as possible. And so instead of a non-renewable hydrocarbon source at the beginning of your pipe, you're putting something that you got from a renewable resource. And that's, in my opinion, a way to transition into an economy that is really not dependent on fossil fuels.
Would it produce more greenhouse effect?
Would it produce more what?
Greenhouse effect.
Yes, the greenhouse effect has not been considered at all in this entire presentation. I mean, finally, if you have a source of clean hydrogen, then there is no greenhouse effect. If you have hydrogen to begin with, you're running that through the fuel cell, and then you do the fuel cell design just like I showed you. The only thing you're producing is water. If you are using a hydrocarbon source, then that carbon has to go somewhere. And so if the carbon goes as CO2, then there's a greenhouse issue. However, if you are viewing this as if you get your hydrocarbon from a renewable resource, like a plant. Now the plant basically took carbon from the atmosphere. It took CO2 from the atmosphere and it made it into a form of stored hydrocarbon. Then all that carbon that the plant took is now being released back to the atmosphere. So in that sense, it's carbon neutral. You're not taking carbon out of the ground and putting it out into the air, which is what you're doing with a fossil fuel. You're taking carbon that was captured millions of years ago and putting it back into the atmosphere at a rate that is higher than the rate in which it went into the ground. So in that sense, you're not carbon neutral. But if you're taking the renewable resource, at least you're neutral. You're not adding any more. But overall, I think that's a good question. We really haven't reduced the carbon. We just kept it neutral if it's renewable.
Okay, sir. There seem to be no more questions. Thank you very much, sir.
Sure. I've also run out of time. So again,